So couple quick announcements. Big one, Canvas Quiz 1 is due at 5 p.m. today. Remember, that's an auto close. Make sure that you've got your submission done prior to that point. Other big one too, midterm 1 is coming up February 10th, 6 p.m. If you're booking with the CFA, please make sure your booking is put in. I will update the required time. The way that we're going to do this for CFA students is start early so you guys can participate in the group section. So do please put that into your calendars. Other one too, and again, some students have asked me this part before. If you're interested in getting involved in undergraduate research, now is your time. This time of year, a variety of programs are starting to pop up. These are the ones that are called the USRA, which are booked through the Department of Chemistry. Chemistry has these, biology has these. This is through both on campus. There's another one called SURE. So there's a whole bunch of these that start to pop up now. These are required where you have to put in an application for them. So these are two quick QR codes from this. These are the ones, the links at the bottom will tell you about those summer research scholarships, both at UBC in general, but also here in chemistry. And there'll be quite a few of these coming up in the following weeks. This is something that start to populate forward as this goes. And I'll try and keep you guys updated as this comes through if you're interested. One more quick part too. Again, I love that you guys have been a lot more interactive. This has been a great, honestly, this has been one of the favorite versions of this class that we've gone through because you guys are asking a lot more questions. I love that. I want you to be interactive in class. However, I need you guys to be respectful to everybody else in the class. If you guys are talking sideways about problem solving and everything else, keep it to a dull roar. There's other people in the class, and if I'm lecturing at the same time, please do not lecture on top of me if you can. If you have to have a discussion about something super cool, or whoever's playing in whatever football match, whatever, out of the class, please. One more point too. Rebecca, I think the front doors are locked. Could you please man those doors for the latecomers and stuff coming in today? Thank you. So we talked last class about enol reactivity, hydrogen deuterium exchange, and halogenation. We're going to go on with that. Quick review reminder. I have two conditions from a ketone. Left and right, I have two different what? These are, if I'm naming these products, their name is a, what do I call this functional group? This is called a enolate, right? So in your own words, what's going on here? How do I select left versus right? So talk to the person next to you. Discuss this. What is happening here? What's the difference between these two? Why am I getting those conditions? Okay, time. If we're going to provide some labels to these two molecules, how might I class them? How might I label them? Or how do I differentiate these two? These, let's say the guy on the right, that might be called what kind of enolate? This is my, what label could I provide to it? Zaitsev. More words, please. Higher substitution. What does that mean, though? In terms of stability, we might say this is more. So that would be considered what? The thermodynamic or kinetic? Yeah, this would be considered my thermo, which is my more stable. Right? More stable may not be forming fastest. It is thermodynamically favored. Cool. That makes the other one my, yeah, the joke. Joke in organic chemistry, especially if you go up for like your comp exam, your oral exam, And if somebody says, what do you think the selectivity mechanism is? You say kinetic. And then they go, oh, that's wrong. Oh, it must be thermo then. It's one of the two. Like, that's it, right? These are opposite pairs between the two. There are cases where they help each other. A lot of the times we use them in opposition. Thermodynamic control, because there's a more stable one. Kinetic control, faster to form, is the least stable one in this case. Why does that match my conditions? So if you look here, hot or cold? Yeah, really, really cold. Anytime you're dealing with kinetic control, cooling things down exacerbates the energy barrier between transition states. Remember, rate kinetics is transition states. So if I have something really cold, I'm trying to limit the energy available to really, really stretch or exacerbate a difference in energy between the transition states. It's under kinetic control. So that's very common. Cold is associated with kinetic control. What about the type of base we have here? LDA, very strong, very weak. This is very, very strong. Irreversible is a usual thing we use with kinetic control. Basically, I'm putting LDA together with my ketone and saying, you get one choice. You get one proton and no takebacks. Pick your proton. And what it's going to do is find the easy accessible one out here, sterics, and more than one. Probability, there's 2 protons versus 1. So kinetic control, especially here, cold, irreversible. Those are the 2 things you're looking for. Under thermodynamic control, warmer, right? Hot, especially relative to these 2, and weaker bases. What we're allowing in that case, something like sodium hydride, is it allows deprotonation to happen, and then basically, wait a minute, maybe I want to go and reset. Now there's a weird thing here, we'll talk about it in more detail. What happens to sodium hydride when it deprotonates? What do you make? Sodium hydride yanks up a proton and it becomes hydrogen gas. Does that sound reversible? Basically, can hydrogen gas give a proton back to my enolate? Probably not. But this is under thermodynamic control. Now again, we'll get into some details about this later. That, for anybody who looks at it and says, that sounds weird, you are correct. Does anybody have a reason? Why is that thermodynamic? Okay, to be continued. We'll come back to this. No, again, we will go through in detail this point. All right, today we're going to talk through oxidations, reductive amination, and the 2 reset reactions. These are ways for us to completely obliterate a carbonyl. This is how we conduct our carbonyl compounds back to our alkanes. So first off, review, oxidation states. Remember this from first year? This is an accounting method to figure out where electrons are distributed, primarily in electronegative bond, where you've got a more electronegative and a less electronegative atom. We're talking about very polar covalent bonds. So in this case, something like a carbon-oxygen bond, what we'll typically do is say, if I have a carbon-oxygen bond, I'm going to say the 2 electrons that are associated with that bond are spending more of their time on the more electronegative atom. So I sort of assign it to that oxygen. Now remember, there's 2 electrons in a bond. In a covalent bond, one came from one atom, one came from the other. Doing this distribution, if I say both electrons in this carbon-oxygen bond are now associated with the oxygen, it's like the carbon is missing 1 electron. Not 2, 1. So a single carbon-oxygen bond counts to a +1 oxidation state on the carbon and a -1 oxidation state on the oxygen. Because I'm taking both electrons and saying, look, oxygen wins. They get that one. One came from itself, so no change, and 1 extra from the carbon, which means 1 missing on the carbon. That's why this would count as a -1 and a +1 in terms of an accounting point, right? We're saying I take the bond, I give it completely to whoever has the higher electronegativity. At the same time, higher oxidation states typically track with more electronegative atoms attaching to that center. So I could look at something and say a carbon with hydrogen, 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 oxygen is at a lower oxidation state than carbon double bond. That counts as 2 carbon-oxygen bonds. This counts as 1 carbon-oxygen bond, and a result of that, lower oxidation state, higher oxidation state, right? Reciprocal is true too. Reduction, or the reduction side of it, is more hydrogens is a more reduced compound or a lower oxidation state. So the counting that you're doing here is carbon to carbon, neutral, no change. They're identical. Carbon to hydrogen, it's more reduced. Carbon to oxygen, carbon to nitrogen, carbon to chlorine, iodine, anything else that's more electronegative is plus on carbon, minus on that center. So overall, during oxidation, we increase the positive density on my carbon. Remember, loss of electrons is oxidation, Leo, and gain of electrons is reduction. So as the oxygen or the heteroatom gains these electrons, it becomes more negative, and as the carbon loses electrons, it becomes more positive. So oxidation will leave behind a more positive center, reduction will leave behind a more negative center. And this is that pairing that goes between the two. But what we're doing here is we're using this as a reactive way to track the kind of reaction that's happening. And again, we focus primarily on the carbon center. So this is kind of the scaffold we have. If you imagine up at the top, alkanes are these guys here. These are the lowest oxidation state because carbons are saturated with hydrogens. They're just carbon-hydrogen bonds. No carbon-carbon double bonds in this point too. As we move over, one oxidation state up replaces one CH with an oxygen. Another oxidation will replace another CH with another carbon oxygen. One more, replacing this one, gets us here, and then the highest oxidation state, CO2. That continuum should be kind of ingrained. You've seen this before, but we're linking them together now. You can slide back and forth, and you need special reactions to go either on the oxidation side or the reduction side. And then there's another one where we can move within the same oxidation state. If you notice, that carbon has the same oxidation state as that carbon. Make sense? How many carbon heteroatom bonds are in the aldehyde? Here we've got 2 times carbon to oxygen or carbon to X. Here, 2 times carbon to X. What it just means is I can move between atoms in the same oxidation state. So if I'm at that sort of that 1, 2, that third level, all the chemistry we've been talking about till now are not changing oxidation state. We're not oxidizing or reducing. We're just perturbing or moving between different permutations of the same oxidation state. Going from a carbon double bonded oxygen to a carbon double bonded nitrogen is the same. We haven't done a redox event. What it also means is, what do you think the oxidation state of, let's say, well, let's do this. R prime H, that guy. What's that functional group? Carbon in the middle, 2 ORs, 1 H, 1 R prime. That is called a acetal. What oxidation state on this list, 1, 2, 3, or 4, is the acetal? How many carbon heteroatom bonds do you have at this carbon? 2. It's the same. These are all iso-oxidation states. What we're doing is we're sliding between them. There's still energetic differences, but we're not going through a massive more hydrogens added to the carbon or more oxygens added to the carbon. These are just perturbations. Why that matters, again, who's burned things before? Okay, I've got you on a list now. That's an energetic process, right? When you combust things, that's what we're showing up here. Taking carbon-based things and burning them makes CO2. That causes all sorts of problems, highly energetic. Lots of energy is released when you do that. Going the other way is really hard too. You got to dump in a ton of energy to do these things. Generally, redox reactions release a ton more reaction or energy than the perturbations. When we're talking about going from an aldehyde to a imine, those are things we can do within sort of relatively mild conditions. But going from an aldehyde up to a carboxylic acid or carboxylic acid down, these have a little bit of a warning label where if you do these things industrially, these are things you want to work out for. These are where you get explosions. These are where you get fires. There's a lot of extra energy that gets associated with them. So they get a special sort of class. Quick review. How do you do each of these? These are 203, 233 reactions. First one to the second one. What am I doing? What's that? So I've got 1 PCC. Everybody agree? Yeah. What's that? Is that the only way to do that one? What else can you do? Jones, PCC or Jones will work, right? We can oxidize this, and because what are we doing? We're taking what kind of alcohol to what kind of product? This is a secondary alcohol becomes a ketone. Do these conditions go any further? Will I over-oxidize this? No, we're stuck, right? I have no more carbon-hydrogen bonds at the center I'm reacting. Okay, down here, how do I do this? Jones is the best choice for this, right? What about this one? That's PCC. So what you guys have the reason we've gone through this is you're doing sort of selective manipulation of oxidation states, stopping halfway, versus ripping all the way through. Those last two, primary alcohols to your carboxylic acids, that's a jump of 2 in your oxidation scale. You go from carbon, oxygen, there's a single, up to 3 versus up to 2. This is where selectivity matters when you're going forward like this. Some are compatible and some are not, just because of this general the state over here. So we're going to focus on this oxidation. You guys know these. The one I want to mention that's relevant specifically to aldehydes is silver. Silver is a reasonable way. You can use Jones and other ones that too, but you can do this one selectively using silver oxide or other silver reagents. One note, the silver 1 reagents are what's called part of a Tollens test. It is a special reaction that happens only with aldehydes or sneaky hidden aldehydes. It is used primarily for sugars, for reducing what we call a reducing sugar, right? If a sugar in its hemiacetal form is wrapped up, that's your sort of your closed ring sort of furanose or your pentose, right? When it opens up, you get an aldehyde form that is formed. That's what ends up reacting. So we're not saying that silver reacts with hemiacetals. What we're saying is silver will always react with the aldehyde center. It's just that that aldehyde center may be connected to some, for example, cyclic hemiacetal. The hemiacetal has spent some of its time in these reaction conditions over at the aldehyde, and the aldehyde is the one that reacts. So why this matters is if you have a molecule that has a hidden hemiacetal, it still will give you a positive Tollens test, and that's what we use for our sugars primarily, for reducing sugars. Going the other way, you guys know this reaction? Carboxylic acid with lithium aluminum hydride. Now, have you guys run into lithium aluminum hydride yet? A little bit? Sounds like sodium borohydride, right? It's the same thing where you've got a salt, lithium or sodium. You've got a metalloid, aluminum instead of boron, but they're in the same row or the same column as each other. It has that same sort of characteristics as sodium borohydride. The difference between it is lithium aluminum hydride is the great reset. It is the big, ugly, dangerous, bad brother of sodium borohydride. Sodium borohydride will not do this reaction, in fact. So I'm making the analogy that it has the same sort of general characteristics and shape. These are both H- type reagents. The big difference is sodium borohydride will look at a carboxylic acid, nah man, I can't do this, tap out. It is not powerful enough, and that's why we have these other reagents. In the same way that PCC is our selective oxidant, sodium borohydride is a selective reductant. The carboxylic acid is so powerful that what we have to do is result to these much more powerful systems. The other one too is important. The other one you've probably done reductions with is palladium over hydrogen. Palladium over hydrogen is a very common one that you've done for doing those reduction reactions. That is primarily, though, for things like aldehydes, ketones, alkenes, double bond things that are lower on our energy scale. Guy like this, as you've done this as you've done this oxidation to make the carboxylic acid, you've made a molecule that's actually not only very stable, but the acidic nature of it actually shuts down quite a bit of other chemistry. So you cannot reduce a carboxylic acid using hydrogen palladium. You cannot use sodium borohydride. You're going to have to use lithium aluminum hydride. But this is where it starts to mix in, where alkenes and stuff like that are also the other side. You can reduce an alkene with hydrogen and palladium. You cannot take sodium borohydride and reduce your alkene. So this is where you've got this orthogonality between these different reactions to help you hit one or another within a different center. The main one we're going to focus on today is a productive reaction, what we call reductive amination. So this is where what we're doing is we're starting off usually with our carbonyls, our aldehydes or our ketones. We're going to be using a primary amine, and we're ending up forming a new carbon-nitrogen bond and a hydrogen. Now note, this hydrogen here, I'll change the color. This hydrogen here you came in with would be this one right here. As part of the reductive amination conditions, we are adding one more hydrogen to that center. Again, we call it reductive amination because there's two things we're doing. Amination, we're making a carbon-nitrogen bond. Reductive amination, we're going from that oxidation state 2 heteroatom bonds like carbon double oxygen down to a single carbon heteroatom bond, one carbon nitrogen. So there's two processes here. Now the way this works, you can do this by first doing the imine reaction you guys are used to. So we can take our aldehyde or our ketone, we can do our condensation under our weak acid conditions, we can stop and form our imine. Once you're at your imine, you can then do your hydrogen metal catalyst one. This is now, remember, aldehydes, ketones, they're in the same state as those other alkenes. Again, alkenes generally will react faster. If you have no other alkenes in the system, you can use hydrogen over palladium to take out your imine. But you have to do this sequential process. We take and we form our carbon-nitrogen center first, and then we install the hydrogen to lock in the goodness, right? What we're doing is we're using that reversibility to switch over from carbon double bonded oxygen to carbon double nitrogen, and then we install hydrogen. Now remember, if you were doing this reduction, you guys would be familiar that H2 adds across this double bond, right? If we do a reduction, what I'm doing is taking my carbon skeleton and I'm adding hydrogen, hydrogen. Well, same thing. There's hydrogen 1, that's hydrogen 2. You're adding across this carbon-nitrogen double bond. So it has the same sort of symmetry that you guys have done through. Now remember, what was special about carbon-carbon double bonds when you add via metal catalyst? Cis or trans? Those two hydrogens end up cis. Same thing here, it's just that thing rotates, right? Any reaction you do on an imine is going to add a nitrogen to that center. Nitrogens, you remember they can parameterize, there's a lone pair. Rotation about this one will hide the fact that it adds cis. I'm just saying it still happens, you just don't see the same thing here because of easy rotation and fluxion around that nitrogen center. There's only one group that won't give you that same cis-trans sort of reaction to them. But it's happening in the same sort of capacity. So that's version 1. What I'm here to tell you is that is the worst way you will ever do it. Organic chemists came up with a far better way. I don't like playing with hydrogen and catalyst. In grad school, somebody working behind me was running a hydrogenation reaction. He thought it was slowing down, so he's like, oh, I will take this flask full of palladium and hydrogen. I think I need more catalyst. Let me open it up to the air, add a whole bunch of oxygen. Now I have catalyst, hydrogen, and oxygen. Boom. Hydrogen gas is not something we love to play with unless we really have to, so we select it for special purposes. Because of that, yes, you can do reductive amination by going aldehyde or ketone to an imine. That's the whole process. I can take my imine and then do a reduction with hydrogen and palladium. Again, taking your life in your hands. Why would you do this? This is a simple scoop pour way where I can do all of that in one step. I don't need to stop and make the imine. I don't need to use hydrogen. This is amazing to do this. But it needs your components, same starting materials, aldehyde or ketone. It works best with an aldehyde, but you can do with both. You take your, usually a primary amine. Now look at the conditions. This, what might you call that? It's right here. It's not sodium borohydride, it's sodium cyanoborohydride. You've got this group attaching into it. You still have 3 times my hydride in there. So there's still hydrides present, but if you had to guess how this stuff is going to react, what do you think? More reactive than sodium borohydride or less reactive than sodium borohydride? Who's on team more? Team less. State your case. Why less? Yeah. What's that? One less hydrogen, that's stoichiometry. But the big thing is, remember, if sodium borohydride is acting like a what? It's a hydrogen donor, H- donor, right? It's a nucleophile. What happens to nucleophiles as you start pulling electron density out of them? More reactive or less reactive? So the sodium borohydride, think of it like BH something. If I put a cyano on it, I'm pulling the electron density out of the boron. I make it less nucleophilic. I'm basically tamping down its reactivity, right? So I'm making it slightly less reactive. More importantly, this reaction really needs protons. It needs an acid catalyst to work, because there's a special thing for this point too. These reactions work by going through this guy. You remember this intermediate? This is my cationic iminium. It's one of the intermediates we generate when we're making imines. As you're forming an imine, this was the penultimate intermediate before you dump that proton. And then you've got a stable imine, which means if I have a slight acid catalyst, I can access this iminium structure. That's helpful. And this does two things. What I've done is I've taken sodium borohydride. Think of it like I took sodium borohydride, H4. It's very reactive, and I made it less reactive by making sodium BH3CN. By adding that cyano, I've basically chilled it out. I made it a little bit cooler. Got a couple beers in him. He's fine now, right? He's not as reactive. On the other side, I took my imine, which would normally be down here, and I've added a proton. I've made it more reactive. So I've taken my imine and I've made it more electrophilic. I've taken my nucleophile and I've made it less nucleophilic. What that does is I've found an intermediate that will only react with my chilled out hydride. I've made a reactive pair where I need both activation of the imine, which can only happen on my imine, and a reactive center that can only react with imines. I've allowed the two to coexist. And why that matters, right? What was the reaction if I took an aldehyde plus sodium borohydride? What happens? Aldehyde plus sodium borohydride gives you alcohol, right? That's a very simple reaction. Aldehyde plus sodium cyanoborohydride, no bueno, nothing can happen. It's not reactive enough to react with the aldehyde. Aldehyde plus acid plus sodium borohydride, again, acid's not acidic enough to protonate my aldehyde, not substantially. So still, nothing happens. But aldehyde plus aldehyde plus amine plus acid, that will allow me to make my iminium. Now that I've got my iminium and my chilled out hydride, they can find react each other. It's a way of staging this so that I can both do the condensation reaction, form my iminium, and then reduce my iminium, which now helps me with Le Chatelier. The imine is now gone. So the reaction can proceed. This is one of those really cool reactions. Honestly, doing this for the first time, you're like, whoa, this is so cool. Especially if you've ever had to make an imine, isolate an imine, go get your hydrogen gas, try to do the reaction. This is a godsend. This is amazing. And it's all because you're matching both tamped down reactivity and activation on both sides. It's a dual activation strategy. How this works is aldehydes plus primary amines, we're going to add my NH across that center. If I take my aldehyde, ammonia in this case, to make my primary imine, aldehyde plus primary amine gives me my NH addition here. And finally, aldehyde plus secondary imine gives me my double substitutions. I can access each of these. So the super cool thing is the same aldehyde starting material can be programmed where I'm controlling what the substitution of the nitrogen is based on what starting material I start out with, right? So I can actually access each of these components, and all allows me to start with the same aldehyde starting material. Substitution pattern on the nitrogen is being controlled by my nitrogen nucleophile. So what do you think happens here? Take this material, carbonyl compound, sodium cyanoborohydride, protons. What's my product? Yeah, take a second to listen. I want you guys to argue this one out because I want you to really, this got to land. If this lands really well, you guys are going to do great on this part. Okay, so let's break this down. When we're looking at these conditions, first of all, first clue, conditions, when you see sodium cyanoborohydride protons, start thinking reductive amination. That's why we use it. If we're doing normal reductions, I wouldn't play around with this. This is what I only use when I'm doing reductive amination. If you're doing reductive amination, I need a carbonyl center and nitrogen nucleophile. So those are my two components. Now, if this was separate molecules, if this part did not exist here in the middle, right, I would take my nitrogen nucleophile, I'm going to add into the center, I do my whole proton ballet. That will give me a ring, which is 1, 2, 3, 4, 5 centers, right? That is the 5-membered ring I think I'm forming. I'm making a bond between my nitrogen and my carbon. I'm going to form right now the iminium form of this. I'm just going to do the condensation. So I want to make a 5-membered ring like this. I'm going to number these off. 1, 2, 3, 4, and 5. Nitrogen 1 also has a methyl attached to it. Carbon 5 was my carbonyl, so that will be my nitrogen double bond. And I still have a methyl attaching to it. So it's this guy. And because it's a secondary amine to start off with, I will have an iminium. This is my iminium intermediate I make. And now, granted, what else can I do with this? Forget about the hydrogenation, or the reductive amination for a second. If this guy was to finish off in a non-protonated way, what would I do? I lose a proton. Yep. It forms an enamine. You're right. This could make a 5-membered enamine in that condensation. But we got these other guys present. It's got another whole life. So not stable. Remember, this is going to be a low concentration. The equilibrium will form a little bit of this. But what makes this possible is we've got a reducing agent that's going to react with this, pull it onto product, which is irreversible, and that will act like drying the sample. It's like using Le Chatelier. We're going to pull the equilibrium forward by reacting this component. So after that whole sort of imine condensation, I get this guy. What's going to happen next is the hydride from this. Think of it like just H- is going to attack that center. And remember, when I'm saying H-, I mean sodium cyanoborohydride. The special thing about that H-, it is a very weak hydride, only reacts with cationic nitrogen iminium species. So only this guy is going to get reduced. It's sitting there waiting for this iminium to form, and then the reduction happens. So when that happens, I'm going to make 5-membered ring, nitrogen, carbon still on here, and I'm going to draw this geometry, methyl up, and hydrogen down, where that hydrogen came from there. Which means, am I going to have another enantiomer? I have an iminium, that's sp2. Hydrogen can add from the top or bottom. I will have 2 possible enantiomers of this. Yes?
Do you need to use a weaker acid so that it doesn't protonate the ketone in the borohydride acid?
So good point. If you went with a strong enough acid, you might protonate your carbonyl. That's a good concern. But look at your molecule. You're still saying, I have an acid. Well, I was going to use catalytic acid, first of all, right? So we're never going in with a ton of acid. We got a catalyst. If I have a catalytic proton, and I have a molecule with a carbonyl and another molecule with a nitrogen, which one's going to win? Which is more basic, my nitrogen or my carbonyl? Nitrogen. Nitrogen's pKa, protonated nitrogen's 9. Protonated carbonyl, -2, -3. So you're right. With a strong enough acid, you might start having a problem. Most of the time, the proton will sit with the nitrogen or through the iminium form only. Like it's kind of tamped out in terms of your concentrations. But again, you could engineer this where if you just whacked in a ton of TFA, yeah, you'll nuke everything. You have another problem when you do that too. Hydrides, sodium borohydride, is functionally a hydride source. With enough acid, you start protonating hydride, you make hydrogen gas, and you're eating glass. That's eventually what's happening too. So it's kind of self-regulating. But the point here is you're going to get both faces adding to the center. We formed the carbon-nitrogen bond in this step here. We formed the carbon-hydrogen bond in the second step. The carbon-hydrogen is added to where? Is it being added to the nitrogen or added to the carbon? The hydride, I mean. That hydride ends up where? It's on the carbonyl. During workup, you're going to add acid and base. The nitrogen may pick up a proton in that sense, right? If it was, let's say, a primary amine. The important thing is the new bond you form from sodium cyanoborohydride, this hydrogen here ends up attaching to where the carbonyl used to be. Which means if I ran this with sodium BD3CN, what we call borodeuteride, where would the deuterium go? Right there. Point is, in the bond you're forming here, this carbon heteroatom bond, the carbon center is your electrophile. It picks up the nucleophilic hydrogen or deuterium. D minus, H minus ends up on that center. If this reaction was run with HDO3, protonated D plus, that would end up on the nitrogen center. So this is a polarized bond where the carbon center is your plus, it's picking up the nucleophile. The nitrogen center is your anionic, it would pick up the proton part of this. Remember, think of hydrogen, H2, as really, you could think of it as hydrogen, 2 molecules of hydrogen, or 2 atoms of hydrogen, H dot. But in a lot of cases, what we're doing here is ionic reduction. It's like taking H2 gas and splitting it into H minus and H plus. The H minus part, the hydride, ends up on the carbon center. The H plus part ends up with the heteroatom if you had that part present. Okay, you're going to go through a bunch of these in the slides after. The last reaction I want to talk about here is what we call a complete reset. If I have a carbonyl and I want to completely obliterate it, I don't want to just reduce it. I want to replace the entire carbonyl with hydrogens, and I want to lose that oxygen as water. So this would be a way where maybe I've installed a carbonyl, I've done a bunch of steps like my enolate formations and something else. I've basically used the carbonyl primarily for the alpha center. I'm using the acidification or the chemical reactivity that carbonyl imparts, but I don't want it in the end. I want to delete it once it's done. This is where you can use the Wolff-Kishner reaction. Here's some cool facts, that's fine. How it works, you take what's called hydrazine and heat, and if you look at this, remember, this is your hydrazone. We introduced this back when we showed you guys your imine. The mechanism for its formation is the same as the imine formation. Your nitrogen center will do a condensation where you're making a carbon double oxygen becomes a carbon double nitrogen. That's the first step. The second step of a Wolff-Kishner reaction is super high temperature. So KOH, high temperature, usually an ethylene glycol. All I want you guys to know are those conditions. If you're doing a Wolff-Kishner reaction, step one, you gotta make your hydrazone. So it's going to be a two-step process. You make your hydrazone with hydrazine. Step two, strong base, high temperature, glyme, you're going to completely remove it. What's happening here, and again, we're not going to cover the mechanism, but what's happening here is that N2, that's nitrogen gas in disguise. How this reaction works is it's through a series of protonations under very strong base conditions that just deletes that carbonyl and replaces it with hydrogens. That's one. Now, like we've shown you to this course, usually organic chemists keep 2 different kinds of reactions in their pocket because these conditions are very, very strong base, super high temperature. If you had another functional group that was sensitive to this base, you're going to destroy everything. So you may need to have in your arsenal an orthogonal reaction that works under acidic conditions. That's this one, the Clemenson. So if you want to do a bond deletion, get rid of the carbonyl, you have two reactions at your disposal. The Wolff-Kishner, its job is to take a carbonyl, make a hydrazone, strong base. Strongly basic conditions will allow you to get rid of that carbonyl under strong base conditions. Downside, any functional group which is sensitive to base that you don't want to destroy, you're also going to nuke it. Your alternative is the Clemenson. And all we do here is I take a carbonyl, I use zinc and mercury metal. It's an amalgam. It's this mixture of these two. This is a dissolving metal reduction under acidic conditions. And once again, hydrogens. This is much more of a radical mechanism. Once again, we're not covering the mechanism. You just need to know the conditions. So, oh wow. It's Friday. What you now have is two different versions that accomplish similar targets under very different conditions. So look at this. If I started with this molecule, what would happen if I use Clemenson conditions? Mercury and zinc under acidic conditions, what's going to happen? Okay. So this is a classic problem. A single starting material. You're applying two different conditions. The top one is your Clemenson, strong acid conditions. Your bottom one, that was a two-step process, strong base conditions. That's Wolff-Kishner. What happens if we apply Clemenson here? I've highlighted the obvious carbonyl. Carbonyls plus Clemenson, everybody should get hydrogens. We have deleted that center. But there is a problem. What else? These acidic conditions are absolutely going to nuke your, what's that called? This is my ketal. Ketal, under acidic conditions, are going to bloop, and it's gone. Same conditions here will temporarily, like you might get this for a fraction of a second, but if you're taking this under strong acidic conditions, again, I challenge any of you to stoichiometrically weigh out the right amount of zinc and mercury, right? This is not something you can do. This is it's a digital reaction. It's on or it's off. You're not going in with selectivity. So that's going to delete this one as well. The product you're going to get under acidic conditions will both hit the obvious carbonyl, but it will also, because you have an acid-sensitive functional group, it will delete that carbonyl, or the second one, because the ketal will become the ketone, which then gets fully reduced, right? So it's a double process through. Bottom one, what do you think happens? The exposed one's still going to get nuked, right? That's still going to happen. What about the other one? Am I sensitive or not sensitive to base? Yeah, it's going to hold on. So if your goal is nuke one and not the other, where you're using an acetal or a ketal protection, Wolff-Kishner is your friend. So this is where, if you go back, we have some other cases where if I wanted to have an aldehyde and a ketone, you should now be able to use a protecting group strategy to protect one and not the other. I can react one and not the other, and I can delete one and not the other through some combination of protection and deprotection. The staging your reactions will give you control to give you something like this, where after that, at my own choice, I could use acid to open that group up and then do more chemistry later, right? It's a way of doing selectivity between them. That's why we have these two reactions, is it gives us more choice. So I'm going to give you another example in the practice, try it later. This is the same kind of thing, but now under a different starting material. Have a great weekend, guys. Okay, so we're going to look at how we might synthesize this molecule using a substituted amine starting material. We're going to use it using reductive amination. So in order to do that, look at your molecule. Reductive amination is going to form one of these carbon-nitrogen bonds. So any of these is a possible starting disconnection. So we could break it across there, or there, which gives us three possible sort of things to evaluate. We could look at it after and say which ones may be more favorable or easier to handle, but let's take each of them in kind. So there, or here. Now in each case, let's do the disconnection across this magenta one. So that retrosynthesis would be from a carbonyl. Remember, that's the carbon-containing center would have been that, and the corresponding amine, right? So that would be this secondary amine. That's this constituent components here. We'd put this together, if you're in the synthesis direction, that's sodium cyanoborohydride under slightly acidic conditions, so like acetic acid in some type of organic solvent. So usually we would do this with a weak acid catalyst, like a weak carboxylic acid species. Okay, let's do the green disconnection. So now we're going to leave the other bonds in place. So it's still a secondary amine, NH, and the single carbon would just simply be formaldehyde. Now, so there's a methyl addition from that center. Let me just reorient that so it's a little clearer. That and formaldehyde. Okay, and our last one, if we were going to do through the blue disconnection, it's this isopropylamine still in place like that, NH, and the corresponding aldehyde left over. If I had to rank them, well, in each of this is the same kinds of conditions. We can use sodium cyanoborohydride and acid catalyst to reform it. If you had to choose among these, generally, if you wanted to do a reactive partner, keeping reactive partners like these aldehydes is somewhat preferable, because remember, you still have to undergo a nucleophilic addition of your amine in order to make that iminium smart. So there's a little bit of a benefit where using a secondary amine and an aldehyde as your partner. Those might be slightly more reactive, but all three are valid in this case. Now, for this one, we're asked to see if we could synthesize this molecule by way of, again, reductive amination, right? So this is where we're going to do is target the bond we would be disconnecting, so it's the carbon-nitrogen bond. And in a similar way as last time, imagine if you broke this bond, retrosynthesis would reduce that to some nucleophilic nitrogen species. In this case, it would be ammonia, is how you would break it out. So there's nothing wrong with that. Remember, the carbon electrophile here would have been a carbonyl. So if we draw that out here, we would have the methyl and carbonyl, and that is not cool. That is a Texas carbon. There's a pentavalent carbon. What's happening here, right, is the electrophilic center here, or what has to be electrophilic center for reductive amination. But you'll notice that every reductive amination, since we're doing an addition using sodium cyanoborohydride, the pieces you're bringing together must include this hydrogen, which is being added as a hydride to some type of a carbonyl center. Right? The reductive amination stitches together your new nitrogen center, whatever that happens to be. You could have two R groups on there. This could have been a ketone as a starting material, but you'll notice that every reductive amination is going to have a hydrogen attached to where that carbonyl center used to be, this carbon here. The nitrogen came in as your other part of your nucleophile. So you can only ever make tertiary centers. Here is a tertiary carbon center with 1, 2, 3 functional groups that are not protons, but you have to have a hydrogen which was delivered through this reductive amination step. That here is delivering in a hydride. So a molecule like we're contemplating here, this one is a quaternary center. There are only carbons and nitrogen attached, there are no hydrogens there. So this could not have been made through reductive amination. So for this one, we're asked a similar question as we did last in class. We're saying Clemmensen conditions versus Wolff-Kishner. Now, once again, both of these conditions, what they do is they delete or completely remove a carbonyl. So that's the same sort of functional group. We're going to react in both cases. I'm going to draw this out where the carbon skeleton through either this guy or Wolff-Kishner is going to be similar. Okay, now both these conditions, neither of them is really going to impact this chiral center. So the methyl geometry is going to be common in both cases. There's really no reason that acid or base is going to impact it. This is not really an acidic center. There's nothing else we're doing. There's no chemistry that can happen there. So that's not going to change. In both cases, we are going to add 2 hydrogens to this carbonyl. No problems there. Challenge comes in right here, that under strongly basic conditions, strong bases are also good nucleophiles, right? Hydroxide like this could potentially do an SN2 reaction. So we'd expect to see an inversion of stereochemistry as hydroxide in the case of the Wolff-Kishner, and the acid conditions will not touch the chloride. Remember, the chloride is a leaving group. It is a negatively charged species, so nucleophile negative species is what we're looking to attack it. What we have over here is strong protons. The protons are not going to impact that group in any substantial way. We're not going to protonate this group and then cause like an SN1, for example. So that's the difference that you'd see here. Is this is an example where we have a base-sensitive group, effectively, or a nucleophile-sensitive group in the molecule, which makes the Wolff-Kishner problematic. Further too, right, even this first step, that hydrazine is also a nucleophile, so you could also say that potentially even that hydrazine step, there's a small chance that we will do, let's say, nucleophilic substitution even there. I'd say much more likely that the second step, this very strong base step, is what we're going to be the major, but the point of it is to identify that under basic conditions, it is possible to disrupt things like these electrophilic centers.